Hello, my name is Trevor Gamble, and my project is a demonstration of photon interference. I'm going to show you a few effects, and we're going to go over what's happening physically and what that implies.
Hello, my name is Shane White.
And I'm Angel Reinders. We're co-students of Trevor, helping out with his experiments. We are responsible for the photography and the cinematography.
My goal in this video is to introduce you to 3 selected physics demonstrations. These will be called wave-particle duality, quantum eraser, and delayed choice experiment. In each, light interference will be used as a visual aid to what's happening. If you don't know the meaning of these phrases, don't worry. They'll all be explained during the video.
This is my setup. It's called an interferometer. It's basically a device that splits a laser beam in half and recombines it at a later place. So, first we have my laser. After that, the laser beam hits the first beam splitter. You could think of it as a half mirror, half window. It splits the beam 50-50. After that, the 2 beams hit 2 mirrors and then recombine at the second beam splitter. Now, I'll show you a pretty cool picture we took of the actual beam path. Enough with the introductions. Let's get to the experiment. As you can see, one of the beam paths is blocked. Also, I'd like to point out this device here in the center of the screen. It's just a lens. We use it to expand the pattern. So, let's see what we have on the screen. As expected, we have a green blob, which is what you should expect from a laser. Now, what I'm going to do is I'm going to take out the cardboard that's blocking the path. Now let's see what we find. An interference pattern. This is evidenced by the dark and bright horizontal fringes. I won't go into light interference as it's not the focus of my experiment, but I will point out that where these dark bands appear is determined entirely at the second beam splitter. Why at the second beam splitter? Because light behaves like any other wave. Like water or sound waves, when 2 sources combine, they interfere with each other. In this case, the sources are the 2 halves of the laser beam. It's well known that light sometimes behaves like a particle and sometimes like a wave. This is the wave-particle duality mentioned before. Only waves have the ability to interfere with each other. Particles don't interfere, they don't have crests, they don't have troughs, nor do they have frequencies. But it is possible to set up the interferometer such that light going through it switches from behaving like a particle to behaving like a wave, then back to a particle. First, we need to dim the laser. We place a device here that dims the laser until we know as an experimental fact that only one light particle is traveling through the device at a time. It would make sense not to expect an interference pattern, as there's no longer a beam of light traveling through the interferometer. It's just a single particle, which should take one path and have nothing to interfere with. But inside the interferometer, the light particle will behave like a wave. We know this because the screen will show an interference pattern. There is a way to get light to behave like a particle inside the interferometer. If we place a detector in each path, here and here, such that we know which path the particle takes, it will behave like a particle, it will take only one path, and we will not see an interference pattern. Why is that? Well, knowing which way the particle went and having it interfere with itself are complementary properties. Complementarity is quantum language for properties that you cannot both have at the same time.
As a recap, we can see that laser light behaves like a collection of individual particles or a standing wave, depending on how you measure and view the laser beam. So if you ask a physicist if the beam of light is a wave or a collection of particles, the answer you'll get is, well, it depends.
With that, we can now move on to the quantum eraser segment of the video.
Let's now look at my second demonstration. The goal here is to make the paths distinguishable. First, to prove that there's no hand waving going on, I'm going to show you what the pattern looks like when the paths are unblocked and indistinguishable. Just like before, we have the interference pattern. The light's interfering at the second beam splitter. Now, I'm going to place a polarized lens in each beam path. One polarizes the light vertically and the other polarizes the light horizontally. Let's see what we get. No more interference. We have two green spots corresponding to where the two beam paths land on the screen.
Let's go over this quickly. The polarizer's job in this demo was to distinguish the light particles traveling through the interferometer by path. And with that, you would not see an interference pattern. This is because it's possible to tell which light particle took which path. Again, being able to tell which path was taken and seeing an interference pattern are complementary properties. Now for the final part of the quantum eraser demonstration. Like before, I have one polarizer in each beam path, one that polarizes light vertically, the other horizontally. These make the paths distinguishable, so there will not be an interference pattern. Now, I'll place another polarizer in the beam path. This one's oriented such that it polarizes the light 45 degrees from vertical, diagonally. Now let's see what we get. It's dimmer, but the interference pattern has returned.
Here's an enhanced photo. On the left side, you will notice that some of the light did not interfere. That was caused by slight misalignment of the polarizers when the video was shot, and is unrelated to my experiment. So, I will ask that you take notice only that the interference pattern returned.
Why did the interference pattern return? Because the third polarizer I placed in the beam path made the two paths indistinguishable. That is, it made it impossible to tell which light particle took which path. Therefore, the light particles again behave as though they took both paths. And how did the third polarizer do this? Well, it repolarized light from each path diagonally, thereby erasing any quantum information that the light particles had that once made them distinguishable. This information happened to be whether the light was vertically or horizontally polarized. This is why we call this demo quantum eraser. Now let's move on to the delayed choice experiment, first thought up by physicist John Wheeler.